Hello, third period. Okay, keep in mind that we saw two examples on Tuesday where we had to adjust the period, and that's because it had the b value, right? It had that value in front of theta. Here we don't have that value, so we're just going to straight out solve. I'm going to take the inverse of both sides, so we have theta minus pi over 4 is equal to the inverse cosine of 1. Okay, so thinking about where cosine is 1 within our 4 quadrants, we end up with theta minus pi over 4 is equal to 0. We don't want to say 2 pi because remember we talked about how it can't be equal to 2 pi. So we'll use the location of 0. Now thinking about what subtracting pi over 4 does to our graph, if we were to graph this, if it's theta minus pi over 4, what are we doing? We're adding pi over 4 units to everything. So in order for us to solve, we're just going to say theta is equal to pi over 4. Now think about our interval, right? 0 to 2 pi. Since this is a cosine function, this is going to occur every 2 pi k, which that's beyond our interval. We only have one solution. All right? So again, if they're adding or subtracting a value to theta, it's that horizontal shift. We do need to check for extra values, but we don't have to adjust the period. Okay, this is the one Josephine was so excited about. So we've got 2 cosine squared theta minus cosine theta minus 1. First thing I want us to do is I want to set a boundary, and I'm going to substitute x in for cosine of theta. And I can do this. I'm just saying let x equal cosine of theta, so I can rewrite this as 2x squared minus x minus 1. In taking out that trig expression, we see a quadratic. Ta-da! Yeah, we've been doing this since Algebra 1, some of you begrudgingly, I'm sure, but it's comforting to know that we know how to do this. I personally am going to use the x method, taking a times c and putting it at the top of my x, and then putting the b at the bottom. Looking for two numbers that multiply to -2 and add to -1, I have -2 and 1. Now, before I go any further, I would like to say, yes, you can solve a quadratic through the quadratic formula or through, completing the square. So this is not the only option, but if it does factor, that's usually the route that I'll take, okay? So since those two numbers add to -1, I am then going to substitute them in for that middle term. So now you've got a quadrinomial. You have a quadratic with 4 terms, or polynomial with 4 terms, meaning we want to factor by grouping. Group the first two, group the last two, and pull out that GCF. So I'm going to pull out a 2x, leaving me with x minus 1, and then the greatest common factor for the last two is a 1. We have to pull something out, so that's what's going to pull out of those two terms, leaving us with x minus 1 and x minus 1. So we have x minus 1 times 2x plus 1 equal to 0. Now, thanks to that zero product property, what do? We set them each equal to 0. And here we remember that we set x to be cosine. So I'm going to choose to substitute cosine of theta back in at this point. Just replacing x with cosine theta, because ultimately that's really what we're trying to solve for. So on the left-hand side, we get cosine of theta is equal to 1. So theta is the inverse cosine of 1, which we actually just saw. We know that it's going to be 0. On the right-hand side, we get 2 cosine theta is equal to -1. Divide both sides by 2, so cosine of theta is equal to -1/2. Theta is the inverse cosine of -1/2. All right, we are not stuck with our restrictions on the inverse. We have an interval from 0 to 2 pi. Cosine's positive in the first quadrant, negative, negative, positive in the fourth quadrant. So we're looking at the second and third quadrants. What reference angle has a cosine ratio of 1/2? That is our 60-degree reference angle, pi over 3. So in the second quadrant, that would be 2 pi over 3. And then we go down to the third quadrant for 4 pi over 3. Making sure at the very end to list all of our solutions. So 0, 2 pi over 3, and 4 pi over 3. Sweet. Okay, for this next one, it says to give a general formula. Okay, we now have 3 different types of directions. First, it said exact value. That means use the restrictions on the inverse. Second, said to solve between 0 and 2 pi. That means we're looking at solutions in all 4 quadrants. General formula means you're looking at solutions in all 4 quadrants, and then you're going to set an expression, an equation that represents an infinite amount. If you need to, pause this video, go back, re-listen, and write that down. Okay, oh, and do me a favor and cross out where it says list 6 solutions. We're not going to do that. No. And I am just going to pretend like it never existed. There we go. Alrighty, so for A, this is what we saw at 4.2. Very straightforward. One trig expression we need to isolate. So I'm going to add rad 3 to both sides. We get 2 cosine theta is equal to rad 3. And then let's divide by 2. So cosine of theta is equal to rad 3 over 2. Taking the inverse, we get inverse cosine of rad 3 over 2. Okay, thinking about our 4 quadrants. Cosine is positive in the first and the fourth, and we need a general formula. So rad 3 over 2 occurs first at pi over 3, and then at, no, I meant 6, pi over 6, and then at 11 pi over 6. This is a cosine function, so it's going to occur every 2 pi k. And we're going to state where k is any integer to represent an infinite amount of solutions. And I'm going to box my answer so beautifully. Okay, for this one, notice, we are going to have a little bit of a period shift, not an issue. Nothing needs to be moved. We literally just need to apply the inverse. So we get 2 theta is equal to the inverse sine of 1. Where is sine 1? Well, around our 4 quadrants, there's only one location, and that's up at pi over 2. Okay, and the function is sine. So how often does that occur? Every 2 pi k. But we're not solving for 2 theta, we're solving for theta. So we need to divide every single piece by 2. This whole thing is going to be divided by 2, just like we've done before. So we find that theta is pi over 4 plus pi k, where k is any integer. Where k is any integer. There we go, and we'll box our answer. Okay, so first we find the solutions around the 4 quadrants, and then we determine how often it will occur. Last but not least, I'd like for you to pause the video and try this one. And in case that theta over 2 is tripping you up a little bit, you can rewrite this as 1/2 times theta. They are equivalent. Okay, so pause the video, please try it, come back and check your answer. Welcome back. Hopefully we are at half theta equal to pi over 4 plus pi k, because this is tangent, and 5 pi over 4 plus pi k. Okay, we're going to multiply everything by 2, so your final answer should say that theta is equal to pi over 2 plus 2 pi k and 5 pi over 2 plus 2 pi k. But take a look at something for a second, please. If we have pi over 2, our first solution, plus 2 pi, and we get common denominators, so 4 pi over 2, what do we get? 5 pi over 2, right, which is our second solution. Tangent is one of the only trig functions, I should say, that has sort of this cool symmetry between its solutions. They're separated by 180. So I have one solution, I rotate 180 for another solution, and then I rotate, and so forth. So you're totally welcome to leave your solution set like that. If that makes sense to you, that's solid. You won't trip up your solution. No area for mistake, leave it. But if you see that you could just put pi over 2 plus 2 pi k, and that's going to include the entire solution set, I am 100% okay with that. If you don't really understand what we just talked about, then don't worry about it. List the two solutions. That's thorough also. Okay, hopefully that was helpful. Whew. Okay, so finishing up that one page, now we're going to move on, my friends, to our identity usage. Okay, notice we're solving twice. Once between 0 and 2 pi, once for all possible theta. Okay, in order for us to somehow solve equations at times, we need to use our identities. And you've been using identities since we've started trig. Tangent equal to sine theta over cosine theta. Cotangent equal to cosine theta over sine theta. Cosecant, secant, cotangent. Those are all fundamental identities that we've been using. You didn't know that they were called that. There wasn't really a reason, but now we need to refer to them as such. The three at the bottom, sine squared plus cosine squared equals 1, and so forth, these are incredibly important. These are called, my screen keeps rolling, the Pythagorean, and I will never ever spell this right. I think that's right. Pythagorean identities. They're important to us with solving. They're important to us for our trigonometric proofs that are coming up. Yes, gasp. You're going to be fine. All right. And they can also be written in different variations. And what you're seeing are the three main. So what we could do for sine squared plus cosine squared equals 1 is subtract. So it could also be used in the format of sine squared theta equals 1 minus cosine squared theta. Or the format of cosine squared theta is equal to 1 minus sine squared theta. The same can be said for the other two, so just take a second, please, and rewrite them in their couple of variations. Same with this third one. Now, if you'd like to know where they came from, how they were derived, let me know. It's pretty cool, and I would love to share that with you. All right, here we go. So when solving, the concept doesn't change, right? We're trying to get theta by itself. But if you're dealing with, in this case, two different trig expressions and you're trying to solve for theta, your goal is to get them to be the same. You might see this in a different light than your neighbor, but when you solve it, your solutions should be the same. I'm going to show you what I mean by that. So first possibility, tangent and cotangent. I know that tangent can be written as sine theta over cosine theta, and that can equal cosine theta over sine theta. Okay, so in changing tangent and cotangent to their fundamental identity, we get a proportion, which we can then cross multiply. So that leaves us with sine squared theta is equal to cosine squared theta. All right, well, they're still not the same, but I remember seeing the squared trig functions, and that's super important because Pythagorean identities, they are all squared. You cannot use them if they don't have the square. Okay, they are all squared. So let's change sine squared theta, using this variation, into 1 minus cosine squared theta. So we get 1 minus cosine squared theta is equal to cosine squared theta. Now we have the same trig function. This is fantastic. Let's add cosine squared theta to the other side. So 1 is equal to 2 cosine squared theta. Divide both sides by 2, so we get cosine squared theta is equal to 1/2. Take the square root, so cosine of theta is equal to plus and minus the square root of 1/2. Don't forget that plus and minus. And we get cosine of theta is equal to plus and minus 1 over rad 2, but we get to rationalize, so it is plus and minus rad 2 over 2. At this point, we're trying to figure out where cosine has a plus and minus, right? 2/2 ratio. There are 4 places because it's plus and minus. So we're going to say pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Those are our 4 solutions. Remember, we're solving from 0 to 2 pi and then all possible. So all possibles, we're going to say theta is equal to, now you can list these out, pi over 4 plus 2 pi k, 3 pi over 4 plus 2 pi k, and so forth. Or if you see that they are separated by pi over 2, you can do it that way also, making sure to state where k is any integer. Okay, so you can either list out all 4 solutions with 2 pi, or if you see that they are consistently separated, in this case by pi over 2, you can do it that way. Okay, so I said, right, that there's 2, maybe 3, maybe 4 different ways to do it. Another thing that you might have seen is that you could rewrite tangent of theta equal to 1 over tangent of theta. Here again, you've got that proportion, so cross multiplying, we end up with tangent squared theta is equal to 1. Take the square root of both sides, so tangent of theta is equal to plus and minus 1. We're looking for where tangent inverse is plus and minus 1, and where is that? Oh, right, it's those solutions. Okay, I know, it's a little bit easier. But again, you're not going to see it the same way as your neighbor, as your friend, as your classmate, okay? Know that there are different possibilities. Yay, so fun with the identities. I know you think I'm crazy, totally okay. We are not dealing with the odd and evens. I know some of the other classes are, we are not, so just cross out B for me, please. And then for C, killing it with the oopsies, change theta, please, to be 1. So 1 minus cosine theta is equal to 2. Okay, take a second, solve for 0 to 2 pi, and then all possible solutions. Pause the video, please, and then come back and check. Welcome back. So hopefully you subtracted 1 divided by a negative and found that inverse cosine of -1 is pi, and then we have pi plus 2 pi k. You don't always need to use an identity. Sometimes they are straightforward like this. Okay, we're going to see lots of variations today. Whoop, whoop. All right, sine squared theta is equal to 2 cosine theta plus 2. Well, I see the squared, which means I can use the Pythagorean identity on the left-hand side. You cannot change cosine theta to be 1 minus sine theta. I'm going to say this a bunch. You cannot use the Pythagorean identities unless they are squared. Okay, so let's substitute in 1 minus cosine squared theta, and now it's equal to 2 cosine theta plus 2. All right, I'm going to add cosine squared theta to the right-hand side and subtract 1. So 0 is equal to cosine squared theta plus 2 cosine theta, and I subtracted 1, so then I have a plus 1 on the outside. Okay, let's see. Does this factor? Well, let's let x, for those that maybe need to substitute in x for a little bit better viewing, set x squared plus 2x plus 1 is equal to 0. Are there two numbers that multiply to 1 and add to 2? Heck yeah, there are. All right, so we can say x squared plus x plus x plus 1 is equal to 0. We're going to factor by grouping. Again, if you use a different factoring method, that is totally fine. I just really like the x method. It's clean, it's mathematically sound, it makes sense to me, but that's me. Okay, everybody has their preference. Okay, so I factored out the greatest common factor, leaving two binomials that were the same. So we actually have x plus 1 times x plus 1 is equal to 0. If you saw that this was a perfect square trinomial and you didn't factor, that's also okay. Nice work. So we have x plus 1 is equal to 0, but we need to remember I have to substitute back in my cosine theta. So we have cosine of theta plus 1 is equal to 0. So cosine of theta is equal to -1. Theta is equal to the inverse cosine of -1. Yes, I'm writing out all of the steps. Hopefully by now, you know that I do that. If you can take the answer from that step, that's fine. You don't have to write the inverse like we've talked about, okay? All right, so we get theta is equal to pi, and theta is equal to pi plus 2 pi k again. Oh, shoot, where k is any integer. I don't think I wrote that on the last one. I would lose points. Oh, no. Ah! The easy points, too. Told you. I always have the small details. Barnacles. Let's fix that, shall we? For those of you that were thinking that on the video, kudos to you. Great job. Thanks for paying attention and listening. I genuinely mean that. For those of you that didn't catch it, hey, I'm in good company. Okay, so we've got C and D. I want to do E with you, and then I'm going to have you try a couple on your own. All right. So, man, they're all different, right? Secant, tangent, cotangent. I'm going to change this. I'm going to change secant to 1 over the cosine of theta. I'm going to change tangent to sine theta over cosine theta. And then I'm going to change cotangent, if I could talk, to cosine theta over sine theta. When you have a bunch of different trig functions, it's a really good strategy to put them all in terms of sine and cosine in the hopes that you'll see some sort of correlation, some sort of connection, okay? I do see that the two on the left have the same denominator. So I'm going to take sine theta over cosine theta and subtract it to the left. Not really sure what's happening. I just know they have the same denominator. So I might potentially be able to combine them, but we'll see. Okay, now I am going to combine them on the left, and the reason being, even though the numerators are different, I can write it as a binomial, and then it's going to give me a proportion. Okay, and for the proportion, all we're going to do is cross multiply. So I have sine theta times 1 minus sine theta is equal to cosine squared theta. This is good. This is really good. And I say this is good because I know that cosine squared theta can be rewritten in terms of sine squared theta. So I feel like I'm a little bit closer to having just one trig function I can solve for. I am going to distribute sine of theta to the quantity. So we get sine theta minus sine squared theta. And let's go ahead and substitute in from the Pythagorean identity 1 minus sine squared theta. Great, 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 great. Okay, so, what's going to happen with my sine squareds? They end up canceling each other out. We get sine theta is equal to 1. How is this so simple and lovely? Yeah, that worked out fantastic. Okay, so where is sine 1 at pi over 2? How often does this occur? Every 2 pi k. Now, it won't always work out where they do cancel out like that, but sometimes it will, just as we saw. Take a little breather, enjoy the moment, write down your solution set. Please be careful, and most of you should write this down. I have a feeling. When solving, you cannot divide through by a trig function. So like right here, I wouldn't divide through by sine of theta. Whenever you divide, it's like dividing through by x. You're losing a possible solution. Okay, so never, never divide. Add, subtract, multiply, absolutely. Never divide. Okay. All right, so if you have questions on these, by the way, please write down your questions and either email me or ask in class tomorrow, okay? We've got F, we've got G, we've got H. I want you to pause the video. I want you to try F, G, and H. We've seen all of these variations before. F has a value in front of theta, so we're probably going to have to adjust the period. G and H are probably going to have to use some sort of Pythagorean identity. Pause the video, come back and check with me, please. Okay, welcome back. Hopefully you tried all three. So F is very similar to what we saw in class on Tuesday. You had to isolate the trig expression, but thankfully it already was, right? So then we just had to solve, and we found that 2 theta is equal to pi over 6 and 11 pi over 6, and these occur every 2 pi k, because the cosine function has a period of 2 pi. Notice over here, where's my pink? There we go. I converted 2 pi to 24 pi over 12, common denominators. That way, when I was changing the period and finding my solutions, I knew what I couldn't go over, what my glass ceiling was. So then dividing by 2, you get pi over 12 and 11 pi over 12 plus pi k. So the first solutions, pi over 12 and 13 pi over 12, come from that first section. And then 11 pi over 12 plus 23 pi over 12. The reason why I got 13 pi over 12 and 23 pi over 12 is because we're adding pi, which is 12 pi over 12. Okay, and don't forget where k is an integer, because I've learned my lesson. All right, for g, since I already had 2 trig expressions with sine, I opted to change cosine squared theta to be 1 minus sine squared theta. That's so I have all the same expressions and I can solve. I subtracted 1 and added sine squared theta from right to left, and then got my quadratic. I decided to factor with leaving sine in the equation. For those of you that wanted to change it to x, that is totally fine. Just remember to put sine theta back in. And then I ended up with these solutions. And I did have to list all 3 out with the plus 2 pi k because they weren't separated by any specific consistent interval. Okay, and then last but not least, I actually went the road less traveled, I think, and I chose to change sine squared theta to be 1 minus cosine squared theta, and I did this on purpose because I had a feeling most of you would change cosine squared theta. So, I wanted to show you that we should get the same solutions, yeah? And looking at this, I had to distribute the 3 into the quantity, and then I got cosine squared theta on the same side, divided by 4, took the square root. Don't forget the plus and minus. 4's square root is 2, so I was able to simplify the denominator, seeing that my solutions are pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. All 4 because it's plus and minus. And then I was able to see if I'm adding pi, right? I'm adding 6 pi over 6. So pi over 6 and 7 pi over 6 are separated by pi radians. 5 pi over 6 and 11 pi over 6, same thing. So I shortened my number of solutions because there was that consistent interval. However, if you want to write them all out, that's totally okay. All right, awesome. Thanks, everyone. See you tomorrow.